because we've been talking about equilibrium, but we haven't done much calculating of equilibriums. Last week we did do this calculation, where you took the equilibrium expression or the law of mass action and you throw concentrations in at equilibrium, and you can calculate the equilibrium constant. But you can also calculate other things, obviously, if you've got one variable missing, or actually in this case, we can express it in terms of a new variable, how much everything should change by. Because if the reaction's proceeding forward, I have to use up reactions and I have to produce products according to the stoichiometric ratios. And so because all of those things move together, if anything changes, everything changes. Even if it is just a little bit. So for an expression like this, we have, or we, I guess, want to calculate the equilibrium constant. And we're given some information in the form of a table. And these are the ICE tables: initial, change, and equilibrium. I mean, they're bolded, but. So we know the initial concentration of A, and we know the concentration of A at equilibrium. And so we can calculate how much it changed by. In this case, pretty easy. It went down by 0.25. So if I used 0.25 molar of A, how much B did I produce? Yes, 0.5. Not just 0.25, but 0.5, because I've got an equation here that says, really what it's saying, if I use 1A, then I get 2B. If I use 0.25A, I get twice as much of that as B, or the product. So this is increases by plus 0.5. And so the equilibrium concentration of B is 0.5. And so we can calculate the equilibrium constant, because K, I'm going to assume these are concentrations, equals B squared over concentration of A at equilibrium. So 0.5 squared over 0.75. .33. And pretty much all of the rest of the math that we're going to be looking at today is using what we know about equilibrium. That equilibrium means that the concentrations are staying the same, the rates aren't the same. Or the rates are the same, the concentrations are probably going to be different, but they're going to be constant at equilibrium. And so if we start out in some condition that's not equilibrium, it will move towards equilibrium. Another example, reaction between carbon monoxide, hydrogen, gas. And we have initial concentrations, and we have at equilibrium, I have 0.11 molar of the product, methanol. So initial, 0.27 molar, 0.49 molar, 0.11 molar. Oh, sorry. I lied. What's the initial concentration of methanol? Zero. It's kind of implied here. It doesn't say it specifically, but because it only gave us the concentrations of two of the things, we can sort of infer that that means that's going to be 0. Some change, and then the ending concentration. And that's where we have 0.11 molar is the final concentration of methanol. So then what we need to fill in again, because in a chemical reaction, right, I can't produce any methanol without using up some hydrogen and some oxygen, or carbon monoxide in this case. So if how much methanol did I make? Not a trick question. Right, that increases by 0.11. So the easy one here is how much carbon monoxide got used. So negative, we used up 0.11, so this decreases, or make it negative, 0.11 molar. That one's easy because the stoichiometric ratio is 1:1. So 1 carbon monoxide, 1 methanol, easy. What about hydrogen? 0.22. Yeah, 0.22, or 2 times 0.11, which is 0.22. And what we're going to do, I don't know, it might even be the next problem, is this amount of change, we generally just call X. So how much did it change by? If we can't figure out directly from initial or equilibrium concentrations because they weren't given, then we say, well, everything changed by X. So if we didn't know exactly how much it changed by, this would be, I'll do it in a different color. Right, we'd say that this is minus X, we'd say this is minus 2X, and we'd say this is plus X. And you can just kind of throw the coefficients in front of that. But because we have numbers, you do 0.27 minus 0.11. So this is 0.16, 0.49 minus 0.22. And that's it. And then our equilibrium constant is going to be 0.11 divided by 0.27 times, not 27. Oh, this one is 0.27. Neat. I'm just going to set that up again. 0.11, 6. So 9.4307. That's right. Yep. I think the tricky part of these problems is the setup. Making sure you know where you can put everything. Once you get it set up correctly, then fill in the blanks and solve. This did actually remind me of, on your labs, even if the question asks, so like on the rate law lab, it asks you to round to the nearest integer, write out your number before you round, then round it and circle that one. Because then it lets me see what you got, and then I can, it's a lot easier to assess, was that the correct rounding? For the last lab, it wasn't that hard. It's 5 or more, or 0.5 or more, you round up. If it's less than that, you round down. Especially something like that, It's not super easy to calculate to make sure. So always write out, and you don't need to write out the pre-rounded number, like the entire pre-rounded number. So like I did here, this is like 9.430 on my calculator. I had 727,023 additional digits, just like 5 or 6. You don't have to go crazy. Okay. All right, so reaction shown. Initial concentration of methane is 0.087. At equilibrium, the hydrogen concentration is 0.012. Find the equilibrium constant. So we're going to have some initial values, we're going to have a change, and we're going to have equilibrium values. What initial values do I know? Initial concentration is CH4. Do I have any other initial concentrations? Can I infer what those initial concentrations might be? Yeah, probably zeros. They're not given, almost definitely 0. And then we can do equilibrium concentration, 0.012. And that's all we know about equilibrium. But we can figure out how much everything changed by, because hydrogen went from 0 to 0.012. Now, yeah, well, we could do it this way. So this increased by 0.012. How much is C2H2 going to increase by? One-third of that. Because hydrogen has this coefficient of 3, that means that for every 2 methane that gets used up, I'm producing 3 of these, but only 1 of those. So I'm only getting 1/3 as much. And we could set this up like stoichiometry if you want. So this is a concentration of 0.012 molar H2. So 3H2, 1C2H2. And so that gives us, oh, we need to divide that by 3. Describing those coefficients from the balanced equation. So 1/3 of that is 0.004. And then how much does the methane change by? .008. And it's going to decrease. Oh, and I guess we should have done this beforehand. But if you think about it, because I was given this initial concentration here, and we can assume that these initial concentrations of the products are 0, we know which way this reaction is going to move. It can only go in one direction. If I have nothing over here, then, oh, we haven't talked about Q yet, but right, the only way this reaction can move is that way, because we have to have some of the products, even if K was really, really small. So that makes this 0.0. I could do it in my head, but I almost always mess these ones up. 7.9. Oh, and now we know this is 0.004. And again, we can relate this all sort of back to x, which is most of the time we're going to be using x to figure these out. So this would be plus 3x. This would be plus x. This would be minus 2x. So x is that sort of like, if it has a coefficient of 1, that's how much it changes by. And then we add those coefficients to multiply and get the amount it changes by. So then this is going to be 0.004, 0.012 cubed divided by 0.078. .78 squared. .136 times 10 to the negative 6, or k is 1.1 times 10 to the negative 6. Any questions so far? Alrighty. So the reaction quotient, or Q. Generally, we use Q to represent what is essentially the equilibrium expression, or if we calculated K, at anything other than equilibrium. It's not necessarily, it doesn't necessarily have to be another value other than K. It could be the same as K. But if we don't know what it is, we calculate it and we say, oh, that's Q. And then if we know what K is, then we can say, well, when Q equals K, that's at equilibrium. So that's this, except that the reaction need not be at an equilibrium. So calculated the exact same way as Q. But not necessarily at equilibrium. And the reason that this is useful is because it's not always obvious which way the reaction will go based on initial concentrations. All of the ones that we've talked about so far, our reactants are 0 or our products are 0, and so it has to go towards the 0, because if there's a 0 in the equation, you can imagine if I had 0 divided by reactants, that's going to be 0. K is always a positive number, so it has to be less than 0. And then if I have nothing in my reactants and I'm dividing by 0, well, that's undefined. So whenever there's a 0 involved, we have to be moving towards equilibrium. We cannot be at equilibrium. Now, if you graph it out, and this graph can be a little bit confusing at first, we've got a simple reaction, A and B, in some sort of, well, in a reaction, a reversible reaction. And over here is the value of Q or K. We actually have K specifically is this red line. So at the red line, that's where products and reactants, concentration of the products divided by reactants is equal to K. And so if we are below that, if Q is less than K, we can calculate for any of these. I kind of wish they had flipped these, because it would be 0.25 divided by 0.75, which would give me a number less than 1. So this is going to move towards the right. And actually, at this point, down here, this is B over A. And what that's saying is I want to get to 1.45. Let's say for this point, so this is 0.25 divided by 0.75, which is going to give me something like a third, 0.33. To move to the right, I need to move molecules. I need to react molecules from the reactants to the products. Because when I'm below that, the products are too small, and the reactants are too, I don't know, I'm just going to use too big. So we move from the one that's too big to the one that's too small. So from the reactants into the products, and that makes Q larger. It means that we move to the right along this graph until we get to K. And then it's the opposite if we are up here, where now the products are too big, too much product, and the reactants are too small. And so, again, we move from the one that's too big to the one that's too small, which will make that number smaller, which will make Q smaller, and then I can move to the left. Moving from products to reactants, moving to the left. Moving from reactants to products is moving to the right. So Q gives us an idea of where we are with respect to K. A lot of the time, it's kind of obvious. Sometimes you might want to calculate Q or need to calculate Q in order to figure out which direction the reaction is going to go. So when Q is less than K, our reaction goes to the right towards the products, because remember Q is, products over reactants. If Q is small, that's because the reactants are too big and the products are too small. And by taking some out of the reactants and putting it into the products, that ratio gets larger. And then if Q is big, that means that the reactants or the products are too big and the reactants are too small. And so we move from the products to the reactants. So Q will, like if a reaction is not at equilibrium, Q will be changing. Q will be moving towards K. And as long as the temperature stays the same, that's the same K. So here we just want to calculate Q, figure out which way the reaction will proceed. Now we can look sort of at these numbers to begin with. So I have K. Is K a large number or a small number here? Small, right? A lot less than 1, 10 to the negative 3, pretty small. So we're expecting to see more reactants or more products? More reactants. Small K means we have more reactants than products. Based on these initial concentrations, can you tell which way this reaction will go? Q is larger or smaller than K?
Larger.
Probably. But we do have, this squared, and since this is less than 1 and it's squared, it'll get even smaller. But this is a perfect example of it's hard to tell. You might guess just based on this concentration's higher, but when I throw it into the equation, this is 2NO, wait, no, I have those backwards. This is smaller than that, but this is going to be squared, so it's going to get even smaller. Maybe I should reverse the numbers on that. Anyways, point being, it can be hard to tell. And Q, as long as you have all of the initial concentrations, is not hard to calculate. So this is NO2 squared over N2O4, which equals I get to use that Jason Bourne quote again, which might also be a golfing quote, but whenever you're doing problems like this where the numbers are not in the order that you may expect them, like the NO2 was given to us first, even though that's the product, just slow down a little bit and make sure that you're putting those numbers in the right spots. So slow is smooth, smooth is fast, because you make fewer mistakes. So now this is going to be .0255 squared. And so Q is 0.019645. Which 3 sig figs so is Q larger or smaller than K? It's actually larger. Yeah. So Q is actually larger than K. And two ways to compare, because I know decimals can be tricky, and especially when you've got something in scientific notation and something not in scientific notation. If they are relatively small numbers, we can just take them and put them both into decimal notation and try to line up the decimal points. So going to be 0.0 is larger than 0.00. The other thing you could do is put them both into scientific notation with the same exponent. So 5.85 times 10 to the negative 3. I could rewrite my 0.0196. If I move this 1, 2, 3, now that's 19.6 times 10 to the negative 3. So putting those, really what we're doing is we're taking the numbers and giving them the same magnitude so that we can line them up and see them side by side and see that, yeah, 19.6 times 10 to the negative 3, obviously larger than 5.85. And so since Q is larger, that means that my products are too big and my reactants are too small. So this will move from products to reactants, meaning that this will move to the left or to the reactants, which means my concentration of products decreases, my concentration of reactants increases. Questions? Okay. If you don't want to ask your questions now, I do have office hours right after lecture, and also from 1 to 2. Okay, so for this reaction, we got partial pressure of 1 for N2O4 and a partial pressure of 1 for NO2. So which statement is true of the reaction mixture before any reaction occurs? So with that initial state, are we at equilibrium? Is Q equal to K, or are we going to go towards the left or towards the right? Yeah, towards the left, because what would Q be? Be 1 squared divided by 1, which is 1. Q is larger than K. So if Q is larger than K, proceeds towards the left. Okay. So we kind of have two, in terms of finding equilibrium concentrations, this is where we use ice tables the most. We got kind of two types of problems. We've got K and all but one equilibrium concentration are known. That was like the first one that we did today. Or was it the first one? Maybe we haven't done those yet. But you've got K, you've got the rest of the concentrations, and so we can just solve for the missing one. So if you got K equals B over A, if I know K and I know A, I can find B. Pretty simple. But sometimes, I would say the much more interesting problem is if we know K and the initial concentrations, and then we need to find how everything changes to get to equilibrium. And that's where we need ice, ice, baby. Dun, 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 dun. All right, so easier kind of problem. We have K, and it says in an equilibrium mixture, the concentration of iodine, I2, is 0.1 molar. What is the equilibrium concentration of iodine? Monoiodine. So to be able to use K, and to be able to use the equilibrium expression, K equals, this would be squared over 2. There's actually a few things that we have to check for. One of them is, do I know the equilibrium concentration of anything? So do I know the equilibrium concentration of anything? We do. A little bit tricky, because it says in an equilibrium mixture. So we're saying, that's saying we're at equilibrium, and at equilibrium, the concentration of I2 is 0.1 molar. So we do have at equilibrium, I2 equals 0.10 molar. The other thing to pay attention to is this is Kc. And so ideally we would use Kc. And because that's Kc, we just have to make sure that we have concentration and molarity and not partial pressure. Because if we were given Kc for this problem, and we were given partial pressures and not concentration, we'd have to do some converting, because this equation has 1 mole of gas on this side and 2 moles of gas on that side. So we'd have to do that RT raised to the change in N, which fortunately don't have to do here because we do have molarity. but I want it to be on your radar, so to speak, thinking about those things in case it comes up. So 0.011 times 0.01. Square root everything. And this should be 2 sig figs. Wait. Oh. Oh, okay. That's interesting.
Actually, is right.
Huh. Wouldn't have expected just an extra 0 to make that big of a difference in the final number. Cool. We're going to get to do, I set this whole thing up because we got to do quadratic formula. Oh, yeah. So same kind of problem. We got some reaction. We know K. So we got Kc is 4.0. We have the concentration of A is 1.0 molar. So Kc, we have concentrations, not atmospheres. We want to know what is the concentration of B. So 4.0 equals B squared over A, which is 1.0. So the square root of 4. B2 equals, whoops, B. Again, those are definitely the easier types of problems. The more common and harder one is where you need to use an ice table to figure out those concentration changes. And this is where I was trying to sort of prime that idea of X in those previous problems. So we're going to represent our changes because we don't know exactly how much everything changes by. We just know that it will change. We can say it's going to change by some amount X and then solve for the amount of change. Because we know at the very end, all of our concentrations in the law of mass action should equal K. So again, using our just ever so classic equation. So we have an initial concentration and we know what K is. So in our ice table, we can say, right, our initial concentration of A, and then this is where we use X. We know A has to decrease in this case because I don't have any B. So there's only one way the reaction can go. And so I can say, well, 1 is going to decrease by some amount X. And that means that B is also going to increase by 2 times the amount that A decreases because of the stoichiometry. 2B, 1A. Sorry, brain was thinking of Nier Automata. The main character is 2b. The 1.0 minus x, so the initial concentration minus whatever it changes by, is what's going to give us the final concentration of A at equilibrium. And then this will be 2x. And then to solve for this, we plug those values. So this will be 2x squared. Actually, let me just use parentheses. Over 1.0 minus x. And we set that equal to the equilibrium constant. Because we know that once these changes take place, these represent the concentrations. And so if I can represent those concentrations, I can plug them in and know that whatever x is going to equal 0.33. And then we always, well, not always, a lot of the time though, you end up with a quadratic. So 0.33 minus x equals, not 2, 4x squared. And we want to get all of that to one side, so we get 4x squared minus, or plus x, minus 0.33. That should be 0.33x. So you could use the quadratic formula. I'm going to show you an easier way, as long as you have the right kind of calculator. These calculators have a quadratic solver. And of course, with quadratic solving power comes quadratic solving responsibility. If in your math class you need to solve quadratic equations by hand, I'm sorry. That's what you got to do. In this class, though, you could use the polysolve, so polynomial solver. It's right there above, what is that, the cosine, inverse cosine. So if I hit second and then polysolve, this isn't going to make it into the video. Yeah.